Hello students, in this video we'll see an example of finding the flow of a vector field over a piecewise defined curve. Let's let C be the following curve. So we're going to be in three-dimensional space, just in the first octant. There's the z-axis, there's the x-axis, and then there's the y-axis. What we're going to do is our curve is going to go from 0, 0, 0 all the way to 1, 0, 0 along a straight line. So a straight line, there's our curve C. Then it's going to go along what? Then it's going to go along the unit circle. So that's the unit circle. To the point 0, 1, 0. And then it's going to go straight along a straight line up to the point 0, 0, 1. So my curve is three pieces. My curve is three separate curves. And so let's label them. So my curve is going to be C1 over here, C2 over here, and C3 over here. Okay? So what I'd like to do is I'd like to do the following. Let's find the flow of the following vector field over C. We're going to look at x plus z, and then y, and then x minus z dot t hat ds. Okay, that's a flow integral. Okay. So now what we're going to do is we're going to say this is actually three separate flow integrals. So let's call this vector field over here v. Then this is equal to, by definition, the integral over c1 of v dot t hat ds plus the integral over c2 of v dot t hat ds plus the integral over c3 of v dot t hat ds. So for this problem, we're going to need to parameterize each of these curves. So let's do so. So to parameterize c1, how will c1 be parameterized? Well, c1 will just be r1 of t, which is going to be t, comma, 0, comma, 0 for t between 0 and 1. It's a straight line segment, so we can parameterize in this way. When t is equal to 0, we're at 0, 0, 0. When t is equal to 1, we're at 1, 0, 0. So this, in fact, is the parameterization. c2, r2 of t, will be, well, it's the unit circle. Our classical thing is to do cosine t, comma, sine t, and then 0, where the z is in the 0 direction. And t goes between 0 and 2 pi over here. That's my unit circle and the xy plane. And finally, c3 is going to be r3 of t. And that will be what? Well, we're doing a line from the point 1, 0, 1, 0 to the point 0, 0, 1. So I can look at it like this. I'll do a 1 minus t at the starting point plus t times the terminal point. And that's going to be a starting point. So the last one's going to be a 0 over there. 0, that's my starting point. And then a 0, 0, 1, that's my terminal point. Here t goes between 0 and 1. Okay? So this r3 will simplify to what? It'll simplify to 0, 1 minus t, comma t. So that's my r3 parameterization. So let's do these integrals one at a time. So what we're going to do for this first integral over here, let's call this one over here 1. We'll call this 2, and let's call this over here 3. Okay? So what will 1 be? 1 is going to turn into the integral from 0 to 1. That's my parameter. Then in my vector field, I'm going to replace x, y, and z with what they are on the curve. So x is equal to t, y and z are equal to 0. So I'm going to have a t for my x, a 0 for my z, and then what's y? Y is 0, so there's nothing here. And then I'm going to have an x minus z, so I'm going to have a t minus 0. So again, another t over here. I'm going to dot that with the derivative of r1. The derivative of r1 is just going to be 1, 0, 0 dt. And so what we have is we just have the integral from 0 to 1 of t dt, which is equal to 1/2. So the first part of the flow contributes 1/2. Let's do the next part of the flow over here. For 2, we're going to integrate between 0 and 2 pi. Let's replace x with what it is. X is cosine t, cosine t. Z is equal to 0. Y is equal to sine t, sine t. And then what's x equal to? X is equal to cosine t. Z is equal to 0. I'm going to dot this with the derivative of r2. The derivative of r2 is negative sine t, and then cosine t, and then 0 dt. So now let's look and see what happens. Over here, we're going to have a negative sine times cosine. Over here, we're going to have a positive sine times cosine. When I dot those things, it's going to give me 0. Those first two terms dot to 0. Then cosine times 0, 0. There's nothing here, so this contributes nothing to the flow. Okay? And finally, let's look at number 3, the contribution of 3 to our flow integral. It's going to be the integral from 0 to 1 again. And now what is x on this curve? X is nothing, so the x is 0. The z is now t, so that's going to be a t for the z. Then I have y. Y is 1 minus t. And then I have x, which is 0 minus z. So minus z would be a minus t. We're going to dot this with the derivative of this curve. What's the derivative of R3? The derivative of R3 is going to be a negative, it's going to be a 0, then a negative 1, then a 1. So I have a 0, then a negative 1, then a 1, dt. And this is going to give us what? So this will be the integral from 0 to 1, nothing. And then a t minus 1, and then a minus t dt. Now the t's are going to cancel. I'm at the integral of negative 1 from 0 to 1. That just gives me a negative 1. So that part contributes negative 1. So all total, what's this flow? So all total, the flow of this vector field over the curve, this vector field has a flow which is negative 1/2, because it's this value plus this value plus this value, which is negative 1/2. Thank you very much.